A single number hangs in the dark like a distant beacon, billions of galaxies. He asks what that number truly counts. From a handful of arc-minutes crowded with ancient sparks to wide mosaics, washed by glare and dust, the ledger forms under thresholds, masks and models. Colours become distances, faint halos fade into background. Early fireflies test the limits of method. He follows photons into catalogues, and the quieter missions they require then turns outward to the sky's uncounted light. The total stands, the mystery deepens, the hunt begins. The headline number sits like a lighthouse on the shore of the unknown, bright, simple, and slightly misleading. It says there are billions of galaxies, an ocean of island universes strewn across the sky. He begins with what that sentence really means. A count is never a direct tally, not when the sky covers about 41,000 square degrees, and the deepest images reach only a few square arc-minutes, a patch on the sky no wider than a fingernail seen at arm's length. Astronomers start with a small area, measure how many galaxies lie within a set range of brightness and distance, and then scale upward to the whole sky. The act resembles taking a thimble of water from a lake and inferring the number of invisible plankton in the depths. Only here the lake expands with time and the plankton glow fade and merge depending on how one looks. A number per unit area sits at the core, a surface density that says how many galaxies appear in a square degree, down to a limit in apparent brightness. That limit is not a casual threshold. It marks a frontier where light falls beneath the combined push and pull of background noise, the glow of the atmosphere for ground instruments, the instrumental signatures in space images, and the long, steady rain of cosmic rays in detectors. When the limit is set, every detected source that looks extended enough to be a galaxy is added to a list. The list becomes a count per area, and the count per area multiplied by the full sky becomes the headline. Yet the steps hide a lattice of assumptions. He lingers on area. The sky is not uniform. Large-scale structure makes some patches over-dense and others sparse. A square degree pointed toward a rich filament or a cluster will yield a higher count than one looking into a cosmic void. Even a deep field chosen to avoid bright stars and known structures lands somewhere in this fluctuating web. The larger the area used to estimate the density, the more these chance differences average out, but the deeper one looks, the smaller the area tends to be. Thus the arithmetic of galaxies marries an urge to widen with a need to go faint, and each choice shifts the result. He turns to depth. Apparent brightness is the currency of detection, but the universe stretches light and spreads it. Distant galaxies not only become fainter in total flux, their surface brightness, the light per unit area, dims steeply with redshift. A galaxy with a long soft halo can fall below the surface brightness floor, even if its core is detected, and a galaxy without a bright core can vanish entirely. The celebrated deep fields taken by the Hubble Space Telescope gather thousands of galaxies in a space no bigger than a thumbprint, yet they still miss structures that glow like fog rather than points. Counting what is seen, and scaling to the full sky, already carries an unspoken phrase down to this limit in these conditions with these criteria. The headline number floats on that phrase. He steps through how the multiplication works in practice. If a deep exposure finds a few thousand galaxies in a few arc-minutes, and a survey finds hundreds of thousands in a few hundred square degrees, those densities weave together into a curve of number counts as a function of brightness. This curve, once corrected for incompleteness, can be integrated to give a total per square degree to a chosen limit. Multiply by the area of the full sky, and the familiar word billions appears. But incompleteness is not a simple fraction. It is a probability that any given galaxy of a certain size, shape and brightness would be detected by the pipeline. Teams build artificial galaxies into their images to see which ones are recovered and which ones are not, and the resulting recovery rate as a function of the properties of the mock galaxies is used to inflate the raw counts. This is where the count shifts from observation to inference. It is honest work, but it rests on models of what typical galaxies look like at the detection edge. If the unseen population differs in shape or colour or clumpiness from the injected models, the correction drifts. He considers the second scaling from the part of the universe sampled by the deep field to the cosmic volume implied by the chosen distance range. Behind the number per square degree sits a three-dimensional census, how many galaxies occupy a slice in redshift, and thus a shell in comoving distance. Photometric redshifts often provide those slices using broad colours to estimate distance, which introduces scatter and occasional misplacements. A misplaced galaxy changes the volume over which it should be counted, and small errors in distance become large when multiplied by the sky. The count grows yet more conditional. The headline number also depends on what is meant by galaxy. The word conjures grand spirals and glowing ellipses, but in the arithmetic it can mean any bound collection of stars, gas and dark matter, whose light passes the detection and classification rules. If ultra-diffuse systems with extremely low surface brightness are poorly recovered, they will not contribute much to the tally even if they are numerous. If tidal debris that may or may not be bound is excluded by design, an entire realm of light remains outside the ledger. If small satellites too close to bright hosts are merged by the segmentation maps, the census leans toward the obvious and away from the hidden. Multiply these small choices by the full sky, and the difference between billions and many more billions emerges from silence. He places the headline into time. Early in the space era, when only a fraction of the sky had been surveyed deeply, best estimates spoke of hundreds of billions. As deeper exposures and improved corrections appeared, the totals climbed. With the arrival of infrared eyes from space, which can see farther back in time and farther into dust, the early universe seemed more crowded than expected. Each recalibration of the faint end of the luminosity function, the part that counts the dim systems, nudged the total upward or downward. The headline number therefore moves with the instruments and with the methods. It is a snapshot of understanding rather than a fixed census. And yet the word billions serves a purpose. It invites the mind to grasp scale. It says the cosmos is fecund, that the night sky holds a number of island universes beyond any plausible survey with eyes alone. The trick is to hear in that word the careful conditions that make it true. It is billions given a brightness limit, given a surface brightness threshold, given a set of recovery tests, given a choice about what counts as a galaxy. The intrigue lies in those givens. They are not flaws but levers, each positioned by necessity. The path from a few arc minutes to the whole sky requires them. He stands the number on its honest base, a density measured piece by piece, multiplied by a sky that dwarfs any single field, translated through a maze of cautious corrections. The lighthouse still shines, but now it reveals the rocks beneath the waterline, and the sea beyond remains larger than the light can show. He now follows the count back to its origin in raw light, because a number is only as firm as the path from a single photon to an entry in a catalogue. Starlight and nebula glow, and the smooth sheen of ancient halos descend through a stack of polished optics, are blurred by the atmosphere if the telescope stands on a mountain, and by the breathing of the observatory even in space, and are collected by electronic sensors that convert energy into charge. The first product is not a picture, but a mosaic of values that record brightness and darkness in a grid. Those values are streaked by cosmic ray hits, peppered by hot or dead sensor elements, and dappled by the faint undulation of the sky itself. To prepare the field, engineers and scientists subtract dark current divide by a flat field to remove pixel-to-pixel sensitivity ripples, align repeated exposures against a lattice of reference stars, and combine the stack while rejecting outliers. The combination hardens the signal and softens the noise, but it also begins to decide what will count as real. A drizzle algorithm or a weighted average privileges certain scales over others, so that a tiny compact knot survives more readily than a broad gentle haze. With the mosaic prepared, the search for sources begins. The pipeline builds a background model, an estimate of the slow glow that fills the field. If that model rides too high, it shaves away low contrast outskirts and intra-cluster haze. If it rides too low, random noise rises into false structure. A detection threshold is chosen in units of the local noise. Above that line an island appears, below it nothing is permitted to exist. The threshold is not a mere number. It is a frontier between being and absence, and a galaxy that hovers near it can flicker in and out, with the smallest change in the background fit. Candidate islands are then grown until their light trails into the noise, and each pixel within the island is assigned to that object. In crowded fields, the islands overlap, and identity becomes a question of partition. Deblending begins. The software traces peaks and valleys in the light, carves the saddle regions into borders, and assigns shares of the ambiguous pixels according to an assumed smoothness. A gentle deblend fuses neighbours into one hiding companions. An aggressive deblend splits a clumpy galaxy into pieces, inventing a family where only one system exists. The choice shifts the census before any astrophysics enters. With shapes delimited, the pipeline measures brightness through strategies that reveal different truths. A fixed circular aperture ignores wide halos and favours compact cores. A growing aperture expands until additional light becomes negligible, but in a crowded field it trespasses into neighbours and swallows stray flux. A model fit chooses a family of profiles and demands that the galaxy conform, then integrates the chosen shape to infinity. A fit can recover hidden outskirts, but it inherits the bias of the chosen family, and can miss warp streams and tidal flares. The measured total light moves onward into the machinery of number counts and luminosity functions, so each strategy imprints a preference across the ledger. Colours are then measured through matched apertures, so that the same physical region is compared in each filter. Colour is the language of distance when a full spectrum is not in hand. From the colours, the pipeline infers a photometric redshift, a distance estimated by how familiar absorption and emission features slide across the filters with cosmic expansion. The estimate carries a range wide for faint and peculiar sources, narrow for bright and familiar shapes. Sometimes the estimate collapses around a wrong value, when a dusty neighbour mimics the colours of a pristine distant system, or when an active nucleus fools the templates with unusually blue or red light. The distance matters because it defines the cosmic volume within which the galaxy is counted, and sets the translation between apparent brightness and intrinsic power. Misplaced distance means miscounted volume. Purity then meets completeness, two goals that strain against each other. The team wants a catalogue that contains real galaxies and excludes noise, but it also wants a catalogue that contains all the galaxies that ought to be there down to a given limit. To assess completeness, the pipeline plants synthetic galaxies in the real images. These ghosts span a range of sizes, shapes, and surface brightnesses, and they are scattered across quiet sky and crowded nests. The pipeline is run blindly again. The fraction recovered as a function of the true properties becomes a table of survival. A compact high-contrast system is recovered with grace. A broad dim system is recovered with reluctance or not at all. The table inflates the observed counts to estimate the unseen. It is careful work, yet it rests on guesses about what unseen galaxies look like at the threshold. If the hidden population is clumpier, smoother or dustier than the ghosts, the correction bends. Alongside completeness runs the culling of contaminants. Sharp point-like detections with symmetric profiles are tagged as stars. Needle shapes and one-pixel spikes are set aside as remnants of cosmic rays. Features that march along detector columns or rows are marked as artifacts. Regions within a certain distance of a bright star or a saturated galaxy are masked altogether to avoid false light. With each cut, the catalogue grows cleaner and also poorer, because unusual galaxies that happen to resemble contaminants are discarded, and faint satellites near bright hosts are exiled by the mask. Confusion waits wherever sources crowd. In the deepest fields, the sky becomes granular with faint smudges until individual profiles overlap like scales. Noise then acquires structure, and the combined glow of countless faint systems becomes a haze that hides the very galaxies one hopes to count. The pipeline must decide whether to split the haze into pieces or to call it background and subtract it away. Either choice removes or invents galaxies at the limit. Only after these judgments does the list crystallize into positions, sizes, fluxes, colors, and distances. From that list, the team builds number counts as a function of apparent brightness, and then as a function of distance. The curves are corrected by the completeness maps and pruned by the purity cuts. The end is a surface density for a chosen limit. Multiply by the sky, and the headline begins to take shape. He sees how many subtle hands touch the tally. He sees that the claim of billions carries a quiet preface that could read as follows: with this background model, with this threshold, with this deblending rule, with this brightness measure, with this redshift estimate, with this completeness table, and with this set of masks. The mystery grows not because the process is careless, but because the universe pours light in forms that resist summary, and the pipeline must be decisive. Every decision is a lens, and through that lens the census assembles itself, precise, provisional, and alive with what it does not quite see. He turns to the ledger where depth and width balance each other like two arms of a set of scales, because the total number of galaxies is carved from choices about how faint to go and how much sky to cover. A pencil beam that plunges deep reaches into epochs when the first systems have only just kindled, yet that same beam samples a vanishingly small fraction of the sky. A broad mosaic that sweeps wide across constellations catches the rare bright kinds that structure the present universe, yet it glides past the faint outskirts and the dim dwarfs that make up the quiet majority. The Hubble Ultra Deep Field, the Hubble Frontier Fields, and the new deep pointings with the James Webb Space Telescope demonstrate what depth can do. In a patch no wider than a thumbnail, they gather thousands of systems, some so red that they likely shine from eras not long after the first stars. The faint arcs of lensed galaxies in cluster fields show how gravity itself becomes a telescope magnifying small and distant sources that would otherwise fall beneath the surface brightness floor. But these triumphs come with a cost that the counting must carry. A single deep field sits within the cosmic web like a pinhole through which a neighborhood is glimpsed. If the pinhole lies near a filament, the neighborhood looks crowded. If it lies near a void, the neighborhood looks sparse. The ledger calls this cosmic variance. Even with careful choices to avoid obvious structures, chance still stirs the total. To reduce that chance, one needs many deep fields in different regions, and each requires long exposure times that grow with the desire to see a step fainter. The signal-to-noise ratio creeps upward like a slow tide. Doubling depth demands a large investment of time and tripling demands more still. Meanwhile, wide surveys such as the Sloan Digital Sky Survey, the Dark Energy Survey, and the NIRCam Subaru Strategic Program map thousands of square degrees with fine but not exquisite depth. They deliver a census of luminous galaxies and clusters across a large fraction of the sky and give the shape of the large-scale structure where walls and filaments interlace like a cosmic foam. In these maps, statistical noise falls because of sheer numbers and local overdensities, and underdensities average out. Yet the shallowness sets a limit. Diffuse halos around galaxies fade into the background. Ultra-diffuse galaxies and low-surface brightness dwarfs are only spotted when exceptionally nearby, and even then many slip away under the glow of the sky and the glare of stars. The two regimes thus count different slices of the population. Depth favours the faint end and the distant dawn. Width favours the bright end and the present scaffolding. The art of building the headline total lies in stitching these slices into a coherent whole. He imagines the ledger balance between two columns. In the depth column, the completeness function is steep because near the limit a small change in surface brightness or size decides survival. In the width column, the completeness is high for bright compact systems, and the shape of the faint tail is extrapolated more than it is measured. The faint tail matters greatly because the luminosity function often rises toward a low intrinsic brightness. If that rise remains steep beyond the limit of a wide survey, the extrapolated contribution of unseen dwarfs can swell the total. If deep fields suggest a turnover, the contribution narrows. Yet those same deep fields occupy small areas, so uncertainty in their slopes couples to cosmic variance and multiplies the doubt. The counting teams respond with hybrid strategies. They anchor the bright end with wide surveys and the faint end with deep fields, cross-calibrate the photometry, and enforce consistent definitions of total light. They also carve the sky into bins by observing conditions because even small drifts in background level, seeing or scattered light change the effective depth. Real surveys are not uniform. Masks bloom around bright stars and around satellite trails. Areas near the plane of the Milky Way suffer from crowding and dust. The usable footprint shrinks and becomes patchy. The true area for counts is thus the geometric area, minus all the masked regions and minus the edges where completeness falls, and that effective area must be carried into the extrapolation. He considers the role of exposure time and filter choice. Deep fields often invest heavily in red and infrared bands to chase galaxies whose light has slid redward with cosmic expansion. But the same emphasis weakens sensitivity to blue diffuse light in nearby halos. Wide surveys choose a fixed set of broad bands to sweep the sky quickly, which sets color baselines for photometric redshifts, but can miss emission features that would declare a low surface brightness galaxy real. The ledger gains and loses in both cases, and the gains in one regime do not simply compensate for losses in the other. Depth saturates on the rarest giants, and begins to fragment them into knots and clumps. Width saturates on the brightest structures, and leaves the outskirts unresolved. He reflects on gravitational lensing as a way to bend the scales. Cluster lenses in programs like the Hubble Frontier Fields push the detection floor downward by magnifying tiny high redshift galaxies, but lensing also distorts areas and can produce multiple images of the same source. If the lens model is imperfect, counts can be inflated by repeats or deflated by missed counter-images. In the ledger, the lensing gain comes with an uncertainty that must be written in the margin. He also reflects on the future meld of depth and width that new missions promise. The Euclid mission and the Nancy Grace Roman Space Telescope plan to tile wide regions of sky with space-quality resolution and infrared sensitivity, bridging the gap between pencil beam depth and ground-based breadth. The Vera C. Rubin Observatory plans to return to the same fields many times, building depth by accumulation while maintaining wide coverage. Each will soften the old dichotomy, but each will still face the old truths of surface brightness, dimming background modelling, and the curation of masks. The heart of the matter stays simple and austere. To count galaxies, one must decide where to spend the most precious currency the observatory owns, which is time. Every hour poured into a tiny field sharpens the picture of the faint majority, but leaves most of the sky unasked. Every hour spent sweeping a new strip of sky strengthens the bright statistics, but slides past the dim outskirts of ordinary systems. The final number of galaxies, when spoken as a single word, is the sum across these choices. It is not a compromise so much as a mosaic where each tile shows a different truth, and only the full pattern suggests the whole. He takes one small patch and asks it to speak for the whole, because the practice of turning a deep field into a sky-wide census is the heart of the headline claim. The Hubble Ultra Deep Field stands as an emblem of this act. In an area scarcely larger than a thumbnail at arm's length, it contains thousands of faint systems distributed across a ladder of distances, each rung reached by measuring the way colours shift as expansion stretches the light. The James Webb Space Telescope has now added its own deep pointings with sharper vision in the red and in the infrared that plucks dim shapes from an earlier era. The problem is simple to state and subtle to execute. One begins by counting galaxies as a function of apparent brightness within the small patch. But the goal is not merely a surface density. It is a three-dimensional census, which means one must also reckon with the slice of cosmic volume sampled by the field at each distance. The volume behind a small solid angle grows with distance like a widening cone, but the useful volume is pruned by detection limits, by the dimming of surface brightness, and by choices about what qualifies as a galaxy. To scale from the patch to the full sky, the team divides the galaxies into bins of distance and brightness, and size constructs for each bin, an estimate of the fraction of objects that would have been detected, given the background level and the instrumental point spread, and then corrects the raw counts upward to compensate for what was missed. The corrected counts per solid angle then become counts per unit, comoving volume when the geometrical factor for that distance shell is applied. Only then, after the correction and the geometric translation, does the multiplication by the total sky occur. The plain arithmetic hides complications that he draws into view. A deep field is a line of sight through structure that is not uniform. Clusters, filaments, and voids decide how many galaxies enter at each distance, and the small size of the field amplifies chance. To address this, teams combine several deep fields dispersed across the sky, sometimes chosen at different ecliptic longitudes to minimize systematic backgrounds, and they compare the counts among them to estimate the size of the cosmic variance. That variance becomes an uncertainty band that is carried with the extrapolation. The band does not shrink to zero with better detectors alone because it is rooted in the geography of the universe, not in the instrument. The next complication lies in the way light moves through filters. A galaxy at a given distance may be bright in one band and faint in another, because its starlight rises and falls across the spectrum, and because intervening gas and dust imprint features that move into and out of the filters as distance increases. To avoid bias, the team constructs selection functions that map which types of galaxies are accessible in which bands at which distances. The function ensures that the count at a given distance is not dominated by only those shapes and colours that the filters happen to favour. Another subtlety is the way total light is measured. A galaxy with a compact core is easily captured by a fixed aperture, while one with a diffuse halo loses much of its light into the background. Model-based measures can recover the outskirts, but may impose a tidy shape on a messy tidal structure. The small patch therefore offers several possible tallies depending on how its light is measured. The safest path is to propagate those choices into the scaling by computing how each measure affects completeness as a function of size and surface brightness, and by carrying the resulting uncertainty forward. He considers the way distance enters twice. First through the colour-based estimate used to place a galaxy in a shell, and second through the translation from apparent brightness to intrinsic power, which is needed for the luminosity function that sets the faint end behaviour. When deep fields rely on colours rather than spectra, the placement in distance comes with a range. Counts in adjacent bins can trade members when estimates move by small amounts. To control this, teams average over the redshift probability distributions rather than fix a single value for each source, an approach that softens spurious features but spreads real features as well. The full sky extrapolation must be honest about this blur. All the while, the map of usable sky is smaller than the literal sky. Deep fields are sited to avoid bright stars whose scattered light would saturate the image, to avoid the plane of the Milky Way, where crowding becomes severe, and to avoid known dense structures if the goal is a field typical of average cosmic density. Wide surveys, which provide complementary information about the bright end, are punched full of holes by masks drawn around bright stars and artifact trails. The total sky area used in the final multiplication is therefore the clean area, not the geometric total, and this distinction carries weight when the final number is quoted. He thinks about gravitational lensing and the trick it plays with areas. In cluster deep fields, magnification reveals intrinsically fainter sources by amplifying their light, yet the same magnification shrinks the source plane area. So a tiny patch in the image corresponds to an even smaller patch in the distant universe. Without careful lens models, one might overestimate the contribution of the lensed population when scaling to the full sky. The balance lies in counting with weights that encode both the magnification and the distortion of area. He then turns to the step from counts to a luminosity function. The shape of this function, particularly at low intrinsic brightness, largely determines how much light lies below the detection floor. A steep rise toward faintness implies that the hidden population contributes heavily to the total number of galaxies, though not necessarily to the total light. Deep fields provide the data points at the faint end, while wide surveys anchor the bright end. Fitting the function requires a choice of form, often a curve that bends from a power law rise into an exponential decline. The chosen form extrapolates beyond what is observed, and the extrapolation feeds the full sky number. A small change in the faint end slope can yield a large difference in the total, and so the uncertainty there radiates through the final figure like a held breath. A final subtlety concerns the background light itself. The sum of known galaxies from deep fields predicts a contribution to the diffuse glow that pervades the sky. Direct measurements of that glow when cleaned of foregrounds sometimes suggest a residual that is not fully accounted for. If that residual is real, and not an artifact of scattered light or zodiacal dust or instrument behavior, it would imply a population of diffuse or distant sources that the catalogues miss. When a small patch is turned into the whole sky, that possibility must be carried forward as a reminder that the scene may be more crowded than the ledger admits. The act of scaling is therefore a braid of geometry, completeness, variance, and method. It is executed with care and with a running reckoning of error, and it produces numbers that are sturdy enough to guide thought and delicate enough to invite revision. The small patch speaks, and the sky listens, and between them the word billions gathers a conditional truth that is no less grand for being conditional. He enters the crowded field where identities are assembled and torn apart because between raw light and final catalogues lies the delicate art of deciding which shapes are one galaxy and which shapes are many. The image is a quilt of faint islands rising from a sea of noise, each island described by pixels that know only how bright they are and not what they belong to. The pipeline begins by tracing the shoreline around every rise above the background model, drawing a segmentation map that assigns every pixel to one object or to none. In quiet regions, the outlines are clear and the assignment is gentle. In crowded regions, the islands touch, merge and interlace, and the assignment becomes an argument that the algorithm must settle. The act of deblending starts with the recognition that a single island can hide multiple peaks. The software searches for local maxima within the footprint, compares their heights, and asks whether the saddle between them is deep enough to justify a split. If the saddle is shallow, the system is treated as one. If the saddle is deep, the system is divided. This simple rule changes the census. A conservative cut preserves unity and hides companions, suppressing the count of small satellites and clumps. An aggressive cut multiplies entities, fracturing a flocculent spiral into a family of shards and inflating the count with parts of a whole. The decision does not occur once, but across thousands of islands, across brightness ranges and redshifts and environments. Within each island, the deblender must also decide how to divide pixels that lie between peaks. A common strategy assumes that each child object is smooth, either symmetric around its center or gently varying. Using that assumption, the algorithm apportions the ambiguous pixels according to how much of the light is likely to come from each child at that location. This assumption works when galaxies present simple cores. It falters when galaxies host star-forming knots, dust lanes or tidal wings that break symmetry. Light then deviates from the assumed smoothness, and real structure is carved away to satisfy a prior. Another strategy fits multiple models at once, letting each child have a chosen profile, while the sum of the profiles matches the observed island. This approach can recover hidden companions and extended halos, but it imports the biases of the chosen family of shapes. A model that expects a smooth disk and a central bulge will miss a lopsided bar and a warped outer ring. A model that expects a compact spheroid will ignore plumes and streams. In both strategies, the segmentation map becomes a mirror that reflects the preferences of the method. He considers the role of the point spread function, the kernel that describes how the instrument smears light. In the deepest images, the kernel is narrow, yet even a narrow kernel blends neighbors at high redshift where angular sizes are small. When two compact galaxies lie closer than the half-width of the kernel, their peaks merge and the deblender must infer a split that the image does not clearly show. At low redshift, the kernel hides within broad structures. Here the challenge is the opposite. The outskirts of giants and the intra-cluster glow are so gentle that they are easily subtracted as background. The deblender then assigns the remaining bright knots to new objects, inventing dwarfs, where there may be star-forming regions in the same system. The problem is made harder by the need to work across filters. Colors are measured within matched apertures so that the same physical region is sampled in every band. But if the segmentation map differs from band to band because peaks grow and shrink with wavelength, the identities wobble. A clump bright in the blue may fade in the red and be lost, while a dusty core may brighten in the infrared and be split from its host. To stabilize the catalog, teams often choose a reference band in which detection and deblending are performed and then measure fluxes in other bands within the resulting shapes. This choice prioritizes the structures that stand out in the reference band and makes the catalogue faithful to some kinds of galaxies and blind to others. He examines the way deblending responds to surface brightness. A diffuse dwarf with no sharp center can fail the peak test and be absorbed into the halo of a nearby host. A thin tidal stream can be chopped into pieces that fall below the threshold and vanish as the background model removes them. Conversely, a giant with patchy star formation can be over-segmented into bright knots, each labelled as a small galaxy. In the ledger, these biases push in opposite directions in different contexts, adding noise to the faint end of the luminosity function and uncertainty to the counted satellites near bright hosts. The team tries to tame the problem with simulations. Synthetic images are built by layering mock galaxies, convolving them with the point spread function, and adding noise that matches the observation. The same detection and deblending code is run on these images. By comparing the recovered components to the truth, the team maps the rate at which mergers are fused, companions are lost and single objects are fractured. These maps then inform corrections to the real counts. The success of this approach depends on how well the mock galaxies capture the messy asymmetries of the real sky. If the mocks are too tidy, the corrections will be too small. If the mocks are too clumpy, the corrections will be too large. He also notes that deblending decides not only how many galaxies exist, but how their light is distributed. When a system is split, the total flux assigned to each child determines where the object falls in apparent brightness, and thus whether it survives cuts for completeness. When a system is fused, the combined light can push it above the limit while eliminating two fainter entries that would have been counted separately. These shifts ripple through number counts and through the fit to the luminosity function. In regions with severe crowding, such as near the plane of the Milky Way, or in cluster cores, the problem reaches a kind of confusion limit, where identity is intrinsically uncertain. Multiple plausible segmentations produce different catalogues with similar goodness of fit to the image. In that regime, catalogues become tied to a chosen philosophy about what constitutes an object. The pipeline by necessity takes a stand. That stand is not arbitrary. It is documented, tested, and defended. Yet it is still a stand, and the headline number inherits it. He lingers on a final subtlety. The segmentation map also defines where the background is measured, because local estimates are often drawn from pixels just outside the object footprint. If the footprint is too tight, real outskirts are subtracted as background. If the footprint is too generous, neighbour light is included as object flux. The geometry of the map thus sets the balance between undercounting diffuse light and double-counting crowded flux. Across a deep field, the cumulative effect of these small geometric choices is substantial. After deblending, the catalogue feels stable. Position, shapes, and total fluxes have names and errors, but the stability is conditional. The same image processed with a different deblender, or with the same deblender tuned to a different aggressiveness, would produce a different list of galaxies and a different set of counts near the limit. This is not a flaw in the craft so much as a reflection of the sky, which offers patterns that sit on the edge between unity and multiplicity. The census must draw a line. Where that line is drawn and how often it's redrawn across the field is part of the hidden story behind the word billions. He now turns to distance because the ledger of galaxies requires more than detection. It demands placement along the long slope of cosmic time. Spectroscopic distance read from a dispersed spectrum where narrow lines and broad breaks mark their rest positions is the firmest anchor. A single confident line fixes scale, and the conversion from apparent brightness to intrinsic power follows without ambiguity. But spectra for every faint smudge in a deep field do not exist because telescope hours are precious, and the sky offers more candidates than slits or gratings can host. The census therefore leans on colour, and colour becomes distance. Starlight bears patterns that evolve with age and metallic content. Young populations glow bluer, older populations redden, and the presence of hydrogen clouds and dust imprints troughs and peaks across the spectrum. As the universe expands, those patterns slide toward longer wavelengths. A set of filters samples the sliding pattern like fingers placed along a harp, and software compares the measured colours to a library of templates built from nearby galaxies and from models of stellar populations with nebular light included. Out of that comparison comes a probability curve for distance narrow, when the features fall cleanly between filters, and wide when degeneracies tie different solutions together. Another path uses training on objects that already have spectra. A model learns the mapping from color space to distance space, and then applies that mapping to the flood of objects without spectra. Both paths turn color into a ladder and let the catalogue climb. He considers what can go wrong. Dust within a galaxy reddens its light, making a nearby dusty system resemble a pristine distant one. Emission lines from vigorous star-forming knots can brighten a single filter and mimic the smooth rise of a continuum that would otherwise indicate a greater distance. Compact, cool dwarf stars within the Milky Way can present colors similar to those of very distant galaxies when only a few broad filters are used. Bright active nuclei inject blue or red power that unmoors the host from any quiet template. Any one of these masquerades shifts a candidate into the wrong shell of volume, and because counts are multiplied by the sky, a small tilt in classification becomes a large tilt in totals. He lingers on dropout selection, the simple and powerful rule that a true distant source vanishes in bluer filters and appears only in redder ones, because neutral hydrogen between galaxies has carved away the short wavelength light. This method has found candidates from the dawn of galaxy formation, but it is vulnerable to imposters. A dusty moderate distance galaxy can lose its blue light and masquerade as a distant object. A cool star can present deep molecular bands that produce the same pattern. Teams counter with additional filters with sharper images that test for point-like shapes, and with follow-up spectra when possible. Even so, the catalogue keeps a fraction of uncertain members whose distance curves remain broad. He talks about priors, the quiet expectations that shape estimates. A photometric distance does not arise in isolation. It can be guided by knowledge of how many galaxies of a given color and brightness are expected at each epoch. This prior can prevent absurd placements and can stabilize solutions when the data are thin, yet it can also enforce yesterday's beliefs. If the prior assumes scarcity at early times, genuinely distant faint candidates can be pulled down toward comfort. If the prior assumes abundance, interlopers can be pushed upward. The choice of prior therefore belongs in the uncertainty budget not hidden behind the curve. He follows the estimate into the act of counting. The census integrates number density across shells of comoving distance. When each source carries a probability curve rather than a single value, the proper method is to distribute its contribution across distances according to that curve. This softens artificial spikes that arise from color degeneracies and spreads real features according to their uncertainty. It also dilutes the contrast of structures, which is honest for photometric maps, but must be remembered when comparing to simulations that carry perfect knowledge of distance. He returns to anchors. Deep programs embed a subset of galaxies with spectra, obtained by slitless dispersers in space, or by slit spectrographs on large telescopes on the ground. These anchors reveal offsets in the photometric method, expose classes of catastrophic outliers, and provide corrections that can be propagated to the full sample. In the search for the earliest galaxies, other anchors appear. Millimeter arrays detect cooling lines from carbon or oxygen that fix distance even when hydrogen lines are hidden by the fog of the early medium. These confirmations sometimes uphold the photometric guess and sometimes overturn it, reminding the ledger that colour is a guide, not a verdict. He examines the role of resolution. Colours are measured within matched apertures so that each filter samples the same physical region. But if the image is sharper in one band than another, a fixed aperture encloses different fractions of the total light and biases the colour. Teams blur the sharper images to match the softest, or they fit profiles to reconstruct consistent total fluxes. Residual mismatches remain for tiny or irregular sources, and those mismatches widen the distance curves. He notes the correction that translates apparent brightness into intrinsic power, for a fixed filter samples different parts of a galaxy spectrum at different distances. That correction depends on the assumed template. If the template lacks nebular emission or an unusually strong break, the intrinsic power can be misestimated even when the distance is nearly right. This dual sensitivity slides objects along both axes of the luminosity function, changing counts at the faint end where the total number is most fragile. He brings Eddington-style bias into view, without the name explaining how noise near the detection limit scatters more faint objects upward than bright objects downward, subtly inflating counts and tilting distance estimates that rely on colour measured at low signal to noise. Teams counter by forward modelling the scatter and by folding it into the completeness and distance probabilities. Even so, a residual tilt persists particularly at the very faint edge, where the claim of existence itself is conditional. Through all this, he sees the bargain that makes the headline possible. Photometric distances open vast samples that no spectroscopic campaign could ever reach. They reveal patterns across cosmic time and uncover candidates from the first billion years. They also pour uncertainty into the ledger, an honest blur that must be carried through every step. The tally of billions is not betrayed by this blur, it is defined by it. The number grows as colour unlocks the deep field, and it wavers as anchors correct the crowd. Distance by colour is the bridge between detection and abundance, and the bridge holds flexible and provisional long enough to carry a careful count into the wide sky. He opens the ledger of luminosity because a true census counts not only appearances but intrinsic power, and the shape of that power across the population decides how many galaxies exist beyond the detection edge. The distribution is described by a smooth curve that swells toward the dim end and thins at the bright end with three features that govern the totals: a characteristic bright scale where giants fall away, an overall density that fixes the height of the curve, and a faint end rise, whose steepness controls the multitude of small quiet systems. If the faint end climbs sharply unseen, dwarfs multiply like grains of sand. If it softens or turns over, the hidden crowd lessens. The task is to measure this curve from incomplete data and then integrate beyond what can be seen. He walks through the ways this is done. One approach tallies galaxies in bins of intrinsic power by estimating the volume within which each one would still be detected given the survey limits. This volume acts as a weight so that bright galaxies visible across larger distances do not dominate the statistics unfairly, and faint galaxies visible only nearby do not vanish. Another approach fits the curve directly by finding the shape that best reproduces the observed distribution, while remaining agnostic about the overall normalization set by the survey area. Both methods must be corrected for the chances of detection that fall with lower surface brightness and larger apparent size. The corrections are learned from injected ghost galaxies and from simulations that push the pipeline to its limits, and the corrections carry uncertainty that swells as the curve approaches the edge of sensitivity. He lingers on the danger near that edge. Noise scatters measured fluxes upward and downward, but there are always more faint objects to be scattered upward than bright ones to be scattered downward. The result is a bias that inflates the apparent number of sources just brightward of the limit. Teams counter with forward modelling drawing mock samples from a proposed luminosity curve, scattering them with realistic noise, and processing them through the same detection steps, so that the fitted curve accounts for the asymmetric shuffle induced by noise. Even so, the last fraction of a magnitude in depth remains treacherous. Small errors in background subtraction in the placement of the threshold or in the measurement of total light can tilt the fitted faint end slope, and small tilts at the slope produce large changes in the total count when the curve is integrated to fainter realms. He considers the complicating role of surface brightness. A galaxy can have modest total light concentrated into a sharp core, or it can have the same total light spread into a broad gauzy halo. The former is favoured by detection, the latter is punished. If the faint population is predominantly diffuse, then a curve drawn from detected sources underestimates their abundance. Deep optical and infrared images even from space pay a tax to this truth, for their background models and their segmentation maps erase very gentle light. Radio and millimeter arrays whisper a different accounting by picking up dust and gas that shine in long wavelengths, even when stars are cloaked. Cross-matches reveal galaxies whose intrinsic power was missed in the optical count because the light was buried in dust or smeared into a low-contrast skirt. Bringing these back shifts the faint end upward without changing the bright anchor points. He turns to distance because intrinsic power depends on how far away a galaxy lies and on which part of its spectrum a given filter samples at that distance. When distances are estimated by colour rather than by spectral lines, the translation from measured flux to intrinsic power inherits the uncertainty of the distance. Templates used to convert between filters and rest frame light also bring assumptions about stellar populations and emission lines. If those templates underplay nebula emission in young systems, intrinsic power is overestimated. If they overplay it, intrinsic power is underestimated. The faint end is most affected because it is filled with small, young, and sometimes extreme systems. He recalls the early returns from the James Webb Space Telescope, where very distant candidates seemed more numerous and brighter than expected. Those claims forced new fits to the luminosity curve at early times, often steepening the faint end and boosting the apparent total number of small galaxies in the first billion years. Later checks with spectra with millimeter line detections and with stricter treatments of contamination have pruned some of the excess, but the message remains that the faint end at early epochs is not yet settled, and that the global count of galaxies depends strongly on where that faint end truly lies. He adds the weight of cosmic variance. The faint end is measured in deep fields that cover tiny areas. The same patch might sit beneath a rich web of filaments, or above a desert of voids. When the intrinsic power bins are filled from such a patch, the inferred slope inherits the chance structure of that line of sight. Averaging across several fields and combining with wider surveys for the bright end helps, but the uncertainty band never falls to zero. He reflects on lensing once more, for cluster fields magnify faint background galaxies and seem to offer a shortcut to the unseen end of the curve. Yet lensing alters both light and area. The same magnification that lifts a source over the threshold shrinks the patch of source plane surveyed, and imperfect lens models can duplicate images or hide counter images. Correcting for this yields a powerful but delicate handle on the faint end one that broadens the possible slopes and reminds the ledger that magnification is both gift and puzzle. He asks what the curve means physically. A steep faint end suggests that galaxy formation proceeds easily into the low-mass regime that small halos gather gas and form stars despite the heating of the cosmic medium and the feedback from their own newborn stars. A soft, faint end or a turnover suggests that suppression wins, perhaps because the first radiation fields cut off gas supply to the smallest halos, or because supernova winds strip galaxies of fuel. The data do not announce a verdict. They deliver a curve and an uncertainty that modelers must explain. The headline number of galaxies inherits this physics by way of the integral under the curve. He closes with a reminder that the luminosity curve is not the same in every band, nor is it the same for every kind of galaxy. Dusty starbursts, quiet spheroids, and disks with widespread star formation each draw their own versions of the curve. The global count that feeds the word billions merges across types and across wavelengths, and in that merge some populations are undercounted while others are overrepresented depending on the survey. The promise of the coming years is a union of deep optical infrared and millimeter maps wide enough to anchor the bright end, and deep enough to anchor the faint, so that the curve can be traced with fewer leaps of faith. Until then, the faint end remains the hinge on which the total swings a slope drawn just above the threshold of sight, upon which rests the size of the unseen nation of galaxies that live below the line. He follows the light as it thins with the stretch of the universe, because a galaxy does not only become fainter in total, it becomes fainter per unit area, and that quiet fact shapes what the catalogues see and what they lose. As distance grows, each patch of the galaxy spreads across fewer photons per square arc second on the sky, and at the same time cosmic expansion saps energy and slows the arrival of photons. The combined result is that surface brightness, the light per unit area, falls away far faster than total light. A compact core can survive this fall. A broad, gentle halo cannot. This is the law that hides low contrast structures and dissolves the outskirts of galaxies into the background even when their integrated power would place them above a nominal flux limit. He moves through the practical chain that follows. The pipeline builds a background model that represents the slow glow of the sky, and that model is subtracted from the image to reveal sources. If the model rides too high, it carves into real outskirts and intracluster sheen, shaving light from structures that are already faint. If the model rides too low, noise features and scattered light rise into false shape. The safest fit is local and smooth, but the local neighborhood of a giant halo can be filled with that very halo, so the model steals light from its parent. Around bright stars, the wings of the instrument response spread light into wide skirts, and these skirts masquerade as diffuse galaxies if they are left unmasked. Teams draw masks and grow them until the wings fall below the floor, but every mask is a blindfold across which real low-contrast systems cannot be measured. When the field is crowded, the sum of many faint galaxies forms a granular fog that the algorithm may treat as background. He points to the sky itself. Ground-based images carry airglow thermal emission and scattered moonlight that vary across the night. Space-based images carry zodiacal light detector persistence and low-level instrumental patterns that drift with time. All of these add structure to the background that must be modelled and removed. The deeper the exposure, the more clearly these patterns appear, and the more carefully the model must be held at bay from the outskirts of real galaxies. In the faintest reaches, even tiny errors in the flat field, the calibration that corrects pixel-to-pixel sensitivity, translate into false gradients that drag down extended light. A corrected halo can be dimmed by a fraction that seems small and yet means the difference between survival and silence. He considers the point spread function the kernel of blur that every telescope and camera imposes. Its central spike is narrow in space, but its wings extend outward, and those wings scatter light from bright cores into the very zone of interest for diffuse features. To unveil true halos, teams measure the wings with bright stars and build deconvolution schemes that attempt to pull back the scattered light. Yet deconvolution is delicate. It amplifies noise and enforces symmetry where nature may be lopsided. If the kernel varies across the field, a single correction cannot cure all. Residual wings can mimic halos, and overcorrection can erase true ones. He looks at galaxies whose identity depends on low surface brightness, ultra-diffuse systems with the scale of a large disk but the glow of a dwarf, tidal streams that mark recent encounters, intra-cluster light that floats between galaxies made from stars that have been stripped from their homes. These structures sketch the slow ballet of gravity, but they are invisible to a pipeline that privileges compact knots. Many wide surveys are optimized for the bright end and for small scales, and their background models and deblending rules work against the recovery of gentle light. Even deep fields in space where the sky is darker and steadier set thresholds that do not welcome the slow rise of a faint skirt. The census therefore favors galaxies with dense hearts, and counts against those whose stars are set far apart. He then steps into the domain of color and distance because the very act of translation from observed filters to rest frame light rewards compactness. A fixed aperture matches across bands, and a fixed aperture captures the core better than the outskirts. Model-based measures can try to recover total light, but the chosen family of shapes often lacks the complexity of real halos with warp shells and streams. At higher redshift, the same physical feature shrinks in angular size, but its surface brightness falls faster still. Halos that are visible around nearby galaxies become unreachable, just a little farther away, and so the average galaxy in a distant bin looks more compact than the average galaxy nearby. The catalogues absorb this illusion and turn it into a trend. He weighs the contribution of dust. Dust does not only hide light, it can also redistribute it by scattering, adding a soft cushion around bright cores that tempts the eye to see a halo where none exists. In the opposite direction, dust lanes crisscrossing a disk break smoothness and cause segmentation maps to carve away parts of a galaxy as background. Both effects tilt the recovery of low-contrast features. He notes that millimeter and radio maps cut through dust and reveal gas and dust directly. These maps often show reservoirs and flows that correspond to faint stellar structures that are invisible in optical images. Where such cross-checks exist, they rescue some diffuse systems from absence. Where they do not, the ledger remains biased toward familiar brightness. He turns to the oldest test, the comparison of distant and nearby galaxies, to confirm that surface brightness really falls with distance in the way expansion demands. Those checks have long supported the idea that the universe expands, and that distant galaxies are indeed dimmed in this particular manner. For the census, the lesson is not the cosmological proof, but the practical cost. The further the reach, the less gentle light can be counted, and the more the catalogue describes only what is sharp. This lesson bleeds into the faint end slope of the luminosity distribution, because many faint galaxies are also diffuse. If they are missed in number, the curve softens. If they are rescued, the curve steepens. He returns to masks and glows. Bright stars and saturated galaxies force the creation of exclusion zones. Within those zones, the ghosts of wings and reflections crowd out any quiet light. Small satellites that would orbit within a few radii of a giant are exiled by the mask. Tidal streams that pass near a saturated core are erased, even when the masks are carefully grown and the lost area is accounted for the environmental dependence of the loss matters. The shadows lie where satellites live, and the census of companions tilts accordingly. He ends with the human choice at the edge of sight. Lowering the detection threshold invites more diffuse light at the cost of more false positives. Raising it purifies the catalogue at the cost of erasing halos and streams. Smoothing the image to reveal gentle structures washes out tiny distant sources. Sharpening it to find the tiniest smudges breaks the surface of broad features into noise. Every deep program finds a compromise and states it in its methods, and then the word billions inherits that compromise without repeating it. Surface brightness dimming is not a flaw to be engineered away. It is the price of looking far into a universe that grows fainter as it expands. The census must live with this price, and carry its consequence in the tally, which is to say, that what is counted is true for what is bright and concentrated, and that beyond that truth, a quieter population waits in the half-light, numerous, persuasive, and presently under the line. He faces the uneven sky because even a perfect instrument and a flawless pipeline cannot make a small patch represent the whole. Galaxies gather along filaments, and walls nest within groups and drop into clusters where gravity knots the web. Great voids widen between these structures, and a narrow beam that pierces the web can meet abundance or scarcity by chance. The ledger calls this sway cosmic variance, and it sits beside the simpler counting noise that comes from small numbers. Counting noise falls as totals rise. Cosmic variance does not fall so quickly because it is written into the pattern of the universe itself. A pencil beam can sample a crowded crossroads or a quiet back road without warning, and the final tally inherits that accident. He traces how the sway enters the census. Deep fields are placed in quiet regions of the Milky Way to avoid bright stars and thick dust, but those careful choices do not free them from the large-scale pattern beyond. One field may look across the flank of a filament that swells the counts at certain distances. Another may look through a void that thins the counts in the same ranges. If either field sets the faint end of the luminosity distribution, the slope can tilt simply because of where the pointing happens to lie. The same fate meets programs that use gravitational lensing, because massive clusters that magnify distant sources sit at special nodes in the web and enrich some kinds of galaxies while impoverishing others. To measure the sway rather than guess it, teams split a survey into many tiles spaced widely enough that structures in one tile do not repeat in another. They compare counts from tile to tile and calculate the scatter beyond what simple Poisson expectation would predict. That extra scatter is the mark of cosmic variance. When sky coverage is limited, they turn to numerical universes in which dark matter grows through gravity and forms halos, and then galaxies are assigned to halos following rules that match what is known. Mock-light cones are cut from these simulations with the same footprint masks and depth as the real survey, and the scatter in the mocks sets the expected sway. The mocks also give the full covariance between bins in distance and brightness, because a single overdensity brightens several adjacent bins together. He notes that geometry matters. Masks drawn around bright stars, satellite trails and saturated galaxies break the footprint into pieces and edges. The window through which the sky is seen has a shape, and that shape filters structures like an instrument that favours certain notes. A filament that runs along the long side of a field will produce a different pattern from a filament that crosses it. The window also hides modes larger than itself, so slow gradients across the sky cannot be measured within a small patch. Analysts account for this by forward modelling the window and by adding a term for the integral constraint, a quiet reminder that the mean density is not perfectly known inside a finite frame. He watches how environment alters not only numbers but kinds. Dense regions are fertile for mergers and for the quenching of star formation, so the mix of galaxy types in a cluster differs from the mix in a quiet field. If a deep pointing lands near a cluster, the faint end may be filled with red compact satellites that would be rare elsewhere. If it lands in a void, the faint end may be blue and diffuse. Translate either case into a global slope without adjustment, and the total number inferred for the full sky will drift. Teams respond by weighting fields according to the large-scale density traced by bright galaxies from wide surveys, or by combining deep beams with broad, shallower maps so that environment can be measured and corrected rather than assumed. He separates cosmic variance from lensing by foreground structure. Even when a tile is free of massive clusters, the gentle sum of matter along the line of sight can magnify some regions and slightly dim others. The change in observed counts depends on the slope of the number counts with brightness. If the slope is steep, magnification lifts many sources over the threshold and increases the count. If the slope is shallow, dimming can win. This effect is small for any one tile but systematic across many, and it can mimic or mute true density fluctuations if left unmodelled. Deep programs now fold magnification bias into their error budgets by correlating counts with independent maps of structure, such as weak lensing shear fields or the distribution of bright galaxies. He considers counts in cells a simple but strong lens on the same problem. The survey is divided into many patches of equal area, and the number of galaxies in each patch is tallied. The distribution of these counts as a function of cell size and depth encodes both clustering and chance. From that distribution one can infer the strength of clustering and forecast the expected sway for yet smaller patches including pencil beams. Applied to deep programs, this method shows that cosmic variance dominates the error budget at the faint end until many widely separated fields are combined a practical guide for where to spend precious time. He follows the sway into the step where number counts are fitted with smooth curves. If the faint end is measured from a single deep field, then the covariance between adjacent distance bins is large, because the same overdensity boosts several bins at once. A fit that ignores this shared rise and fall claims a false precision. Modern analyses therefore propagate full covariance matrices into their likelihoods and test the sensitivity of results to plausible changes in that matrix. They also perform jackknife resampling, removing one tile at a time and refitting, to see how much the answer depends on any one line of sight. He notes how the sky can be made more even by design. Deep programs now scatter their pointings across both hemispheres and across a range of longitudes so that no single supercluster dominates the sample. They coordinate with wide surveys to share photometric scale and masks, making the stitching cleaner. They also climb into the infrared, where zodiacal glow is smoother and where the backgrounds are steadier, which reduces spurious gradients that could be mistaken for real structure. Yet he also notes a limit that no design can overcome. The universe contains modes of structure larger than any finite survey. Those very long waves modulate the mean density within the footprint by a small amount that cannot be measured from inside the footprint itself. This supersample sway sets a floor under the uncertainty that remains even when counting noise is tiny and calibration is excellent. The headline number must live with that floor. He ends by turning the unevenness into part of the message. The same clustering that frustrates a census is the imprint of growth from tiny early ripples under gravity. Deep fields that disagree are not in conflict. They are reports from different neighborhoods of the web. The careful census acknowledges this and speaks in ranges that include the sky's own variation. When it says billions, it is an average over a textured dome rather than a polished constant. The wonder is that even with this sway with fields that rise and fall by chance, the sum across many views converges. The ledger accepts that convergence with humility carries its uncertainty honestly, and moves on because the goal is not to remove the sky's pattern, but to understand it well enough that the word billions keeps its meaning while the web keeps its beautiful uneven truth. He walks into the hidden quarter where dust and glare rule because a large share of galaxies live behind veils that ordinary optical surveys do not pierce. Dust is not simply an obstacle. It is the rerouter of starlight. Young stars pour energy into their birth. Clouds and grains of carbon and silicate absorb the short wavelength light and reissue it in the infrared and the millimeter. A galaxy that would look modest in visible light can blaze in the far infrared, and when the sky is mapped, at long wavelengths, a different census appears. Instruments aboard space observatories and on high and dry plateaus reveal sources that are nearly invisible in deep optical images. The Atacama Large Millimeter and Submillimeter Array sees compact knots of dust heated by intense star formation, while wide-field cameras in the infrared collect a softer background glow from countless faint emitters. These populations alter the ledger in two ways. They add galaxies that are missing from optical catalogues, and they change the ratio of star forming to quiet systems at the times when the universe was most fertile. He follows the first path. A single bright dusty galaxy at moderate distance can sit undetected in an optical catalogue, if dust absorbs nearly all starlight shortward of the near-infrared. Photometric redshift methods built on blue and red filters will fail to recognize such a source. Yet the same object shines strongly in the submillimeter, where long wavelengths pass through dust with ease. The identification game is difficult. The beams of many long wavelength surveys are broad, so a single bright submillimeter detection often blends light from several optical sources. Without interferometric resolution, the counterpart remains uncertain, and the inferred distance and power wobble. When interferometers sharpen the view, they sometimes reveal that the bright spot is actually 2 or 3 compact galaxies in close company, each contributing to the flux. The catalogue then gains not one galaxy but several, and the local density spikes for that small field. He follows the second path. The total power radiated by dust across the sky known as the cosmic infrared background sets a ledger-wide constraint. The sum of known infrared galaxies should account for that glow when foregrounds are subtracted. For years, measurements have suggested that a significant part of the background remains unresolved into discrete sources, implying a crowd of faint dusty galaxies below individual detection thresholds. Stacking techniques which add together many images centered on the positions of faint optical sources draw out an average long wavelength signal and reveal the hidden contribution of objects that are invisible one by one. These stacks suggest that the everyday star-forming galaxies seen in optical deep fields carry more dust and more hidden star formation than their colours alone would imply. He considers the role of mid-infrared spectral features, broad emissions from complex molecules that brighten certain filters at specific distances. When those features slide into a survey band, selection becomes strongly favoured, and when they slide out, the same galaxies drop below the limit. Counts in the mid-infrared therefore oscillate with distance if corrections are not applied. Proper treatment uses templates that include these features, and ensures that the census does not exaggerate or suppress populations simply because a luminous spectral feature aligned with a band. He turns to the ages when the universe formed stars most rapidly, roughly a few billion years after the beginning. At those times, dusty starbursts were common, fed by streams of gas and by frequent encounters. Optical deep fields recover the companion population that is less obscured, but long wavelength maps reveal the heavy workers. Without these maps, the ledger undercounts galaxies and misjudges the distribution of star formation across mass and time. The Nancy Grace Roman Space Telescope and the Euclid mission plan to add wide, sharp infrared imaging that will narrow the gap, and interferometers in the millimeter will continue to resolve bright sources into individuals, but even these will face confusion where the sky is crowded by many faint emitters whose beams overlap. Confusion introduces a flaw to sensitivity that longer exposure cannot wholly breach. Deconvolution and probabilistic association help, but they import assumptions that must be carried into the error budget. He notes another cloak, the glare of the Milky Way and of bright foreground galaxies. Dust in our own system layers cirrus like smoke across the sky, and scattered light from brilliant stars throws halos and spikes that corner the detection of faint smudges nearby. In the halos of massive galaxies, diffuse starlight and extended wings drown the signals of satellites that would otherwise be counted. Radio maps show that gas and dust continue far into these halos, hinting at faint stellar counterparts that optical surveys cannot secure. The census of companions therefore runs low, especially within a few radii of giants. He connects dust to color-based distances. A dusty galaxy at moderate distance can mimic the colors of a pristine far-distant candidate, particularly when only broad filters are available. This confusion lifts counts in the early universe if imposters enter the high redshift bins, and it suppresses counts of dusty galaxies in their true epoch. Cross-checks with millimeter line detections and with radio continuum maps that trace massive star formation without dust bias pull the threads apart, confirming some early candidates and reclassifying others. Where such cross-checks are sparse, the ledger carries an extra line of uncertainty. He follows the energy. A basic accounting asks that the starlight absorbed by dust and re-emitted in the infrared should be balanced against the ultraviolet and optical light that is missing. In individual galaxies, energy balance models fit both sides and recover a consistent star formation rate and dust content. For populations, the sum over many galaxies should match the measured backgrounds if selection effects are well understood. Present measurements approach this balance but do not quite close it, leaving a gentle tension that hints at either residual foregrounds in the backgrounds or a population of diffuse or distant emitters that continue to elude the catalogues. He returns to what this means for the word billions. The unseen dusty population is most numerous in eras favoured by long wavelength selection, and the census is most robust where multi-wavelength maps overlap. Outside those overlaps, the count by sight alone is incomplete by construction, and the miss is not small. Dust hides not only light but identity, and it produces a parallel universe of galaxies that must be called into the tally by instruments that do not rely on the visible. The intrigue is not an accusation but an invitation. It says that the sky when read only in starlight tells half the story, and that the other half glows at longer wavelengths where the cold interstellar medium carries the heat of young stars. The ledger grows more honest each time a dusty knot acquires a distance and a name, and the total number of galaxies grows with it, reshaped by populations that the eye alone would never count. He steps into the glow around the bright because the census is most fragile where faint companions huddle beside giants and where diffuse light spreads between galaxies and clusters. A single, luminous host can cast a wide field of scattered light whose wings mimic the gentle halos the team hopes to measure, while at the same time those wings drown the very satellites that would complete the ledger. Around stars within the Milky Way the problem is commanding. diffraction spikes and reflections lay down rigid geometry that masks patches of sky, and the background model that follows those features pulls high to compensate, shaving away any low contrast object that lies within. Around bright galaxies, the problem is softer and more insidious. The core lifts the nearby background, the instrument spreads a long skirt of light that falls only slowly, and the outer isophotes of the galaxy itself extend farther than the eye expects. In that mix, small satellites with low surface brightness slip below the detection floor, and tidal streams that carry evidence of recent accretion are carved into noise. He watches how pipelines respond. They draw masks around saturated stars and around luminous galaxies, and they grow these masks until the wings sink below a chosen level. The chosen level protects purity and stabilizes photometry for the remaining objects, but it also creates dead zones in which satellites cannot be counted at all. When masks are small, false structure enters. When masks are large, real structure is barred. Analysts propagate the lost area into their surface densities and into their errors, yet the loss is not uniform across environments. Satellites live near hosts, so the masked zones overlap the very places where satellites should be found. He examines the deblending of bright hosts. A giant with patchy star formation can be fractured into knots and rings, and the algorithm may label some knots as separate galaxies. The opposite fate is more common. The diffuse wings of a host swallow a nearby dwarf, and the segmentation map assigns the shared pixels to the larger object. In crowded groups and clusters, the light between galaxies intracluster light, made from stars torn from their homes, covers the field like a veil. Background models designed to subtract smooth glow erase this veil, and with it the submerged satellites that ride within. In such regions, the completeness of the catalogue does not simply fall with total brightness, it also falls with distance to the nearest bright neighbour and with the local diffuse intensity. Teams measure this by injecting synthetic dwarfs at many radii from real hosts, and by counting how many survive. The survival fraction plummets within a few effective radii of the host, and recovers only slowly. Counts of satellites that do not include this suppression will run low, and the faint end of the luminosity distribution will soften and tilt. He pulls at a thread that links missing satellites to a long-standing tension. Simulations of structure formation in the dark matter framework predict that halos of all sizes should bring forth many small subhalos, countless potential homes for dwarfs. Observations around the Milky Way and around nearby giants find many small companions, but not as many as the earlier simulation suggested. Part of the difference has been reconciled by the understanding that not every small halo can form stars after the early heating of the cosmic medium, and by the recognition that the most diffuse dwarfs were previously absent from surveys. Yet a significant part is observational geometry. The glare of hosts erases dwarfs near the very places where they are most common. As low surface brightness searches deepen, and as pipelines tune to protect diffuse light, more of these companions appear, and the tension eases though it does not vanish. He considers satellite colour and shape. Dwarfs in the glare are often quiescent, their gas stripped by tides, and by the hot atmosphere of the host's halo. Their light is red and smooth, their cores are modest and their outskirts are gentle. Every trait weighs against their recovery. Conversely, blue star-forming clumps can survive as separate entries even when they belong to the host, inflating the count in a different way. The error therefore swings both above and below the truth-changing sign with radius and with morphology. He looks into the halves of clusters where intracluster light is strongest. In these regions, smooth models are subtracted to reveal individual galaxies, but the models often assume symmetry and monotonic decline. The true light can contain shells, ripples, and bridges that a symmetric model cannot fit, and the mismatch settles into the background and is subtracted away. What remains are sharp cores and compact companions that fit the favoured shapes. A census drawn from these images will undercount the debris of past interactions and the very extended galaxies that live on the edge between bound and unbound. To address this, teams craft special background models that assume an even larger scale smoothness and allow for a low-order representation of intracluster light to survive. They also use wavelet methods that separate structures by scale, preserving slow variations while isolating compact sources. Each method has limits and tastes, and the catalogues they produce differ in the same fields when the emphasis shifts. He follows the trail into photometric distance. The colours of a faint satellite measured against the raised background near a host are uncertain, and so the estimate of distance widens. Some satellites are pushed behind their true shells and become field galaxies in the catalogue. Some background galaxies strongly reddened by dust slide toward the host and become false satellites. Spectroscopic follow-up is hardest near the bright centres that cause the confusion because the scattered light degrades the signal to noise in slits and fibres, and the number of available apertures is limited to begin with. Millimetre observations that pick up cold gas add a second route to distance for gas-rich companions, but many quiescent dwarfs have little or no gas, and the cross-check cannot reach them. The ledger therefore carries an extra uncertainty line for satellites large, precisely where the galaxy ecosystem is most interactive. He notes a step that rescues some of what is lost. Image stacking around many similar hosts builds an average halo and reveals the faint outlines of common companions and streams. The individual dwarfs do not reappear in these stacks, but their collective signal confirms that they exist below the threshold of single detection, and guides the design of searches that integrate longer, or that adopt tailored filters to emphasize expected shapes. He points ahead to surveys that combine sharp images with repeated visits. Frequent returns let analysts build and subtract a better model of the instrumental wings and scattered light, and they help identify transient artifacts that otherwise pattern the background in static stacks. Future space maps in the near and mid-infrared will also ride above much of the glimmer that haunts ground images, softening the glare, but not eliminating the need for careful masks and cautious deblending near bright hosts. He ends by nesting this problem inside the headline number. The word billions depends on a census that is blindest in the crowded places where gravity does its most intimate work. The unseen dwarfs and the subtracted streams live in the shadow of light that the pipeline must control but can never fully conquer. Every year brings better models of wings and better protection for diffuse structures, and every year adds satellites to the rolls. Yet the sum still leans against brightness, and the full population near giants is not yet safely in hand. The count grows more honest as the glare is tamed, and honesty requires this admission that what lies closest to the bright is also closest to being lost, and that what is lost there shifts the total in ways a global average alone cannot repair. He enters the first billion years where the census strains most because the earliest candidates push every method to its limit and invite both excitement and caution. The James Webb Space Telescope assembles deep images that reach redder wavelengths than earlier eyes, allowing the search for galaxies whose light has been stretched so far that only the infrared remains. The simplest rule, the dropout rule, says that a true distant source disappears in blue filters because neutral hydrogen along the path absorbs short wavelength light and then appears in redder filters with a sharp color break. That rule has guided selections for many years, and now reaches into an epoch when the universe is still young and the background medium is partly neutral. In the first months of the new images, catalogues filled with candidates that seemed too numerous and too bright compared with comfortable models. The faint end of the luminosity distribution at early times appeared steeper than anticipated, and the bright end seemed fuller. If taken at face value, these counts suggest that small galaxies formed stars rapidly, that feedback from newborn stars did not shut down formation as strongly as expected, and that the supply of cool gas was more abundant or more easily gathered. He holds those possibilities but walks through the hazards. Colours at the faint edge are measured with modest signal to noise, and strong emission lines from vigorous star formation can brighten a single filter and imitate a continuum that belongs to a more distant object. Dust within a moderate distance galaxy can dim the blue and redden the overall slope so that it enters the same selection box as a truly distant source. Compact cool dwarf stars in the Milky Way carry molecular features that can mimic the dropout pattern. Lensing by foreground structures can magnify interlopers and raise them above the threshold in a way that preferentially selects certain kinds of spectra. Each of these imposters raises the raw counts of early galaxies and must be weeded by sharper images, by more filters, or by spectra. The strongest anchor is a spectrum that shows a rest frame ultraviolet break at the correct place, and when fortune allows emission from ionized oxygen or hydrogen with the expected offsets. Obtaining such spectra for the very faint is demanding. Slitless modes in space risk confusion in crowded fields, and slit spectrographs on the ground struggle with the density of airlines and with the weakness of nightly windows. Even when a break is seen, care is needed, because a dusty galaxy at moderate distance can present a similar break in broadly sampled data. Millimeter observations with the Atacama Large Millimeter and Submillimeter Array add a second route to confirmation by detecting cooling lines from singly ionized carbon or doubly ionized oxygen. A secure line fixes distance without reliance on ultraviolet color. Some of the earliest claims have been confirmed this way, and others have been reassigned, showing that the first rush contained both truth and enthusiasm. He looks at sizes. Early candidates in the infrared appear compact close to the point spread function. That compactness helps detection, but also makes classification more vulnerable to confusion with stars and with unresolved blends. Lensing by clusters presents candidates that are even smaller and brighter, but lens models must be accurate to avoid double counting multiple images and to correct the source plane area. In several lensing fields, reanalyses have revised magnifications and reduced counts. The tally moves first one way, and then another as models and data converge. He follows the star forming histories implied by the early candidates. If numerous galaxies are already luminous, only a few 100 million years after the beginning, then either their star formation is extremely efficient, or their initial mass functions tilt toward massive stars that brighten early. Yet early dust detections toward some candidates show that heavy elements exist already, arguing for prior generations of stars. Balancing these facts involves assumptions about gas inflow-outflow and the press of radiation on newborn clouds. The counts cannot by themselves decide these questions, but they set strong boundary conditions that models must respect. He raises the issue of ionized hydrogen lines and how they affect photometry. In young galaxies, these lines can be very strong, adding power to bands that sit near the rest frame optical. When translated back to intrinsic power, these lines can masquerade as a strong break from old stars, pushing estimates of stellar mass upward and of specific star formation downward. The cure is spectra that separate lines from the underlying continuum, or careful template sets that include line emission. Until the cure is applied widely, The inferred distribution of mass and the shape of the luminosity curve in the earliest bins remain movable. He threads cosmic variance into the story once more. The fields that reach these epochs are small and often chosen to avoid nearby defects in the instrument or in the background. A single overdensity at a given distance can swell the counts in one field, while a neighbouring field equally deep misses that wave. Tiling across the sky reduces this sway, but time on the deepest programs is limited, and the earliest bins remain vulnerable to chance. He considers the balance between purity and completeness, conservative selections that require a strong dropout signature and clean morphology produce purer samples, but miss faint or dusty early galaxies. Inclusive selections that accept weaker breaks and allow compact blends produce larger samples with more imposters. Teams often publish both a strict and a loose list and carry their difference into uncertainty. The strict list tends to see a steeper faint end because it privileges compact blue objects, while the loose list brings in more red dusty systems that are harder to confirm. He watches how the sum of early candidates matches the diffuse background light. If the number of faint early galaxies implied by steep faint end slopes were taken to a very low limit, the integrated light could exceed what is measured. This tension is usually softened by recognizing that not all faint galaxies form stars with the same intensity per unit mass, and by recalling that selection at early times is biased toward star-forming systems. Quiet dwarfs with low surface brightness do not shine in the ultraviolet, and are likely missed entirely, shifting the true energy budget. He notes that even the definition of a galaxy is strained here. Small clumps in growing halos can be counted separately in images that split them from their parent even though they are not yet independent systems. Other times a compact group of small galaxies may be fused into one by the deblender and assign the properties of a single object. The assignment changes the counts in the brightest bins at early time where a few objects carry much leverage. He ends with the reason this frontier matters to the headline. The total number of galaxies across the sky depends sensitively on the faint end slope at early epochs, because the accessible volume in those shells is vast when multiplied by the area of the whole sky. A gentle steepening brings millions upon millions of additional dwarfs into the fold, while a softening eases them away. The reality at the dawn era is still being written by new spectra, new long wavelength conformations, and new models that revise contamination and lensing. The honest position today is that early counts are higher than once comfort allowed, but not as extreme as the first wave suggested, and that the balance between purity and completeness decides just how much higher. The word billions leans into this uncertainty with care, acknowledging that the first billion years are a moving target and that each new anchor can swing the faint end and the total in step. He opens the double ledger that keeps theory and observation in dialogue, because a census of galaxies gains strength when it is checked against independent measures and against universes grown in calculation. On one page lie maps and catalogues built from light from deep fields and wide surveys stitched together across wavelengths. On the facing page lie simulations that start from early ripples in matter and evolve forward under gravity hydrodynamics and recipes for how gas cools form stars and is driven outward by young stars and by central black holes. Semi-analytic models paint galaxies onto the history of dark matter, halos using rules tuned to match a few key relations. Numerical hydrodynamic simulations form galaxies directly within bubbles of the cosmos, carrying gas, and stars cell by cell or particle by particle. Each approach writes its own prediction for how many systems exist as a function of intrinsic power and time, and for how they cluster on the sky. He compares pages. In the nearby universe, the bright end and the overall clustering are well recovered by several families of models. The match falters at the faint end and at early times where the pace of small galaxy formation and the severity of feedback are least certain. Observers bring the latest fits to the luminosity distribution, including the tentative steep slopes suggested for the first billion years by infrared deep fields, and they run forward models that scatter intrinsic power by the measurement uncertainties and apply the same detection limits as the surveys. In that way, theory and data are compared in fair light. When the model produces too few faint galaxies at early times, its recipes for star formation efficiency or for the supply of cool gas are revised. When the model produces too many faint galaxies late in time, its winds and heating are tuned to suppress formation in the smallest halos. The iterations are neither guessing nor overfitting. They are the process by which the free functions of complex physics are bound by richer data. He places a second cross-check on the table, the diffuse background light that fills the sky. If one adds up the contribution of all known galaxies measured in deep fields and integrates below the detection floor with a chosen faint end slope, the sum should approach the measured glow after foregrounds have been removed. In the near-infrared and optical, this cosmic background is difficult to isolate because zodiacal light and instrument scatter are strong, yet multiple methods converge on a value with guarded error bars. In the far infrared, the background is more securely measured by space missions cooled against the sky. In both regimes, the resolved fraction from catalogues falls short by an amount that has narrowed but not disappeared. Some of the residual is surely due to populations just below individual detection thresholds that are nevertheless present in stacks. Some of the residual may be due to very low surface brightness outskirts and intracluster light that are counted poorly in catalogues but contribute to the diffuse sum. A remaining slice could be due to background subtraction systematics in the measurements themselves. The tension serves as a standing reminder that the ledger of discrete sources does not yet close perfectly with the ledger of diffuse power. He adds a third check that does not depend on starlight at all. Maps of neutral hydrogen picked up by radio arrays trace the cold gas reservoir out of which stars form and reveal structures that may lack luminous counterparts in optical surveys. Cross-correlation between these gas maps and the positions of known galaxies measures how much of the gas lies with catalogued systems and how much may reside in diffuse structures that are not yet counted as galaxies. Similar cross-checks pair gravitational lensing shear fields, which trace the distribution of total mass with galaxy counts, to ensure that the observed clustering amplitude matches the mass scaffolding on which galaxies hang. Where the amplitude differs, either the bias of galaxies relative to mass has been misestimated, or the counts fail to represent the full population in that environment. He examines recalibrations that follow from these comparisons. When simulations are tuned to match updated faint end slopes at intermediate times, they often predict a steeper rise in the number of dwarfs around massive hosts than older versions did, which then refocuses observational searches on crowded halos where surface brightness selection is cruel. When background light measurements imply more diffuse power than catalogues can supply, surveys push toward lower surface brightness limits with careful flat fields and improved models of scattered light, and they recover extended halos that extend the light profiles of ordinary galaxies farther than formerly assumed. These recoveries do not usually change the count of galaxies, but they adjust the accounting of light which feeds back into energy balance models and into the translation between ultraviolet light and star formation rates. He writes down a tension sharpened by the James Webb Space Telescope. early reports of abundant luminous galaxies at very high distance demanded either an early and efficient conversion of gas into stars or a tilt toward massive newborn stars that would brighten populations without demanding huge stellar masses. Simulations responded with versions that include rapid early cooling along thin streams, and with feedback that is delayed in small halos. Later confirmations and reclassifications ease the extremes, yet the net result remains that early formation was brisker than many models had allowed. The next wave of calculations now lands closer to the latest catalogues, but the shared error bands remain broad. He notes that agreement is not a final verdict, because different parameter sets can produce similar counts while predicting different internal structures or different histories. That is why cross-checks must be plural. He brings attention to the role of selection functions, the maps that describe what kind of galaxy would be detected in a given survey, as a function of size, surface brightness, color, and distance. Only when simulated catalogues are passed through the same selection, functions can theory and observation be compared honestly. The same applies to masks and to sky windows. A simulation with perfect knowledge of the true mean density must still be filtered through the footprint of a real survey, so that cosmic variance and integral constraints are matched. He ends where the two pages meet. The headline number of galaxies is most persuasive when it sits at the crossing of several independent lines. Counts in light matched by counts in simulation pass through the same pipeline. Diffuse background power matched by the integral of resolved and extrapolated sources across wavelengths. Gas and mass maps that confirm the environments where catalogues claim abundance or scarcity. The crossing is not exact. It is a region on the page where lines nearly intersect and where each year they draw closer. The word billions lives in that region. It is large enough to hold the differences that remain and small enough to be meaningful. The wonder is that such a complex universe allows any closing of ledgers at all. The humility is that the gap that persists is a guide pointing to faint populations not yet tallied to diffuse light, not yet secured, and to early times not yet anchored by spectra. The census advances by following that gap, and the number that is spoken grows more precise as the pages turn together. He opens the black box of the pipeline because before galaxies can be counted, they must pass a gauntlet of rules that decide what enters the catalogue and what is quietly set aside. Every survey begins with a philosophy of detection and a list of quality flags that protect the integrity of measurements. Those flags are necessary, yet each one draws a boundary across which some real galaxies fail to pass. He walks through the boundaries. Source detection requires a minimum number of adjacent pixels rising above a threshold in units of local noise. That rule rejects isolated spikes from cosmic rays and hot pixels, but it also rejects tiny high redshift galaxies whose light is crammed into only a few pixels. Deblending demands that peaks stand tall enough above saddles to be split, a rule that avoids overfragmentation of clumpy disks, but it also hides small satellites pressed into the skirts of their hosts. Photometry demands that saturated cores be masked, and that objects too close to masked regions be excluded, a rule that avoids corrupted fluxes, but it also exiles companions that live precisely where masks are thickest. Star and galaxy separation relies on shape and colour. Point-like sources with colours that follow stellar sequences are labelled as stars, saving the galaxy list from contamination, but cool dwarfs with unusual molecules. Compact galaxies and faint lenses can be swept into the star bin and lost. Colour-based selections used to find special populations such as early universe candidates, or emission line-rich galaxies carve neat boxes in colour space. Objects that fall near the edges wobble in and out with small errors and unusual spectra that do not fit the template lie outside the box and vanish. Quality cuts extend beyond detection. Objects with poor shape fits with suspicious ellipticities or with high chi values in model fitting are often discarded to ensure robust structural measures. Extended galaxies with tidal features that defy simple models then receive poor fits and exit the sample. Objects with blended neighbors can be removed to stabilize colors, a rule that purifies photometric distances, but that rule also removes galaxies in the very environments where neighbors are common, biasing against groups and clusters. He considers the brave new aid of machine learning, which learns from labeled sets to separate stars from galaxies, to flag artifacts and to estimate distances. These models inherit the tastes of their training data. If the training set lacks ultra-diffuse galaxies, the classifier will learn that such shapes are improbable and will weight against them. If the set underrepresents dusty compact galaxies, the model will dislike their colors and push them aside. Even when performance metrics are excellent, they speak of success on the training distribution. The sky is wider than any set. He follows the path of cross-matching between surveys. Multi-wavelength catalogues join optical infrared and millimeter detections by position and by expected colors. The matching uses a search radius, a likelihood score, and sometimes a prior on how many counterparts are expected. In crowded fields, true pairs are missed and false pairs are made. Distant galaxies magnified by lensing can be associated with the wrong optical source in the foreground. Compact groups can be fused into a single long wavelength source and assigned to the brightest member. The unmatched remainder fall out of the joint sample and cease to influence the combined counts. He looks at masks and metadata. Regions with bright satellite trails, ghost reflections, or scattered light are flagged and removed wholesale. Entire columns or rows of detectors with unstable behavior are dropped. The sky area used for counts shrinks by 1% here and 1% there, and within the remaining area edges are trimmed where exposures are shallower. The apparent uniformity of a survey is achieved by excising the messy parts, and with them go galaxies that happen to live in those places. Analysts correct totals for the lost area, but they cannot correct for galaxies whose properties are correlated with the conditions that triggered the cuts. He turns to reproducibility and versioning because pipelines evolve. New flat fields recalibrate the background by fractions of 1%. New kernels describe scattered light more accurately. New deblenders handle crowded scenes with greater grace. With every version, fluxes move, shapes change, and faint sources appear or disappear. Catalogues carry version numbers, yet headline totals often carry only a single figure. A census that is stable under pipeline change inspires confidence. One that swings requires a calm explanation. He examines the practice of flag stacking in which samples are required to pass many cuts at once, to ensure purity for a specific science case. A safe sample for structural evolution may demand well-measured sizes, isolation from bright neighbors, and high signal to noise in several bands. Such a sample will underrepresent satellite-rich environments, ultra-diffuse galaxies and dusty systems. When number counts are derived from safe samples without reweighting, to account for the discarded classes, the totals lean toward neat galaxies in neat places. He notes the triage of visual inspection. For the most delicate selections, humans inspect candidates and remove artifacts missed by code. Human eyes are excellent at spotting ghosts and diffraction spikes masquerading as sources. Human tastes are also real. Inspectors favor symmetry, dislike ragged shapes, and have less patience for extremely diffuse smudges. Unless the process is blinded and randomized, the inspected sample can drift toward conventional beauty. He folds in the role of priors once again. Photometric distances and model-based photometry use priors on expected colors, sizes, and profiles. When data are weak, those priors pull estimates toward familiar classes. Rare galaxies are then pushed into common bins, and the faint end of unusual populations is suppressed. He suggests remedies that are already underway, selection functions that map the probability of detection and survival through every cut in the pipeline as a function of size, surface brightness, color, and environment, allow analysts to weight each detected galaxy by the inverse of that probability, recovering an unbiased total on average. Forward modeling that draws synthetic skies from simulations runs them through the same pipeline with the same flags, and compares recovered to input populations exposes where the pipeline is blind. Open catalogues that preserve near-threshold sources with clear flags rather than hard removals invite alternative cuts tuned to different science. Cross-surveys built with independent instruments and different philosophies of masking and deblending reveal which absences are instrument-specific and which are universal. He ends with the point that is easily missed. The word billions is the harvest of a field that has been carefully planted and weeded. The weeding is essential to keep false detections from overrunning the rows, but it also removes real plants that do not fit the neat image of a typical galaxy. The missing ones are not errors, they are the other half of the truth. The next counts will improve not only by deeper exposures and wider maps, but by pipelines that are honest about their tastes, that measure their own blind spots, and that let multiple philosophies of selection coexist. Only then will the ledger approach the universe it seeks to describe full of neat spirals and ragged streams, blue knots and red ghosts, companions in glare and dwarfs, adrift all present in proportions that the sky not the pipeline decides. He looks forward across the near horizon of instruments because the next eyes promise not only sharper images and wider maps, but also new habits of honesty about what is missed and why. The Euclid mission spreads space-based resolution across thousands of square degrees and pairs, optical clarity with near-infrared reach, so that diffuse halos, red galaxies and tidal debris can be traced in one coherent ledger with stable backgrounds and uniform masks. The Nancy Grace Roman Space Telescope prepares panoramic imaging and slitless spectra in the infrared turning color-based distance into a network of anchored redshifts over wide fields, rather than a chain of guesses hung from a few small beams. The Vera C. Rubin Observatory plans a long cadence that returns to the same sky again and again, building depth by patience, while also mapping the breathing of the background and the slow wings of scattered light, so that models of the sky glow can be tuned without carving away the outskirts of galaxies. In parallel, long wavelength arrays expand their grasp. The Atacama Large Millimeter and Submillimeter Array resolves dusty star-forming knots and cool gas in systems invisible in the optical, while new survey instruments in the millimeter and the radio prepare to measure cooling lines and neutral hydrogen across degree scales tracing cold fuel where starlight is too faint to guide the way. Together, these facilities change the shape of a census. Wide, steady infrared imaging rescues dusty galaxies from absence and pulls red satellites out of the glare of their hosts. Repeated visits learn the signatures of ghosts and reflections and give background models the confidence to spare low-contrast halos. Slitless spectra across large areas create dense lattices of secured distances that bind photometric estimates and compress their uncertainty. Radio and millimeter maps reveal gas-rich dwarfs and obscured starbursts beneath the optical floor, and cross-correlations with optical positions confirm which faint smudges are real members of the ledger. He imagines pipelines that doubt themselves by design. Every night, synthetic skies enter the raw stream seeded with artificial galaxies, that spans sizes, surface, brightnesses, colours and environments, so that completeness is measured under the exact conditions that produce the field and not from a laboratory of convenience. Deblending is learned against a symmetry trained on ragged shapes and tidal wings, rather than only on quiet profiles, so that the default decision is no longer to split clumps and fuse halos. Machine learning aids are trained on deliberately unbalanced sets rich in oddities, and are calibrated in full simulations before they are trusted on the sky. Catalogues preserve near-threshold detections with clear flags rather than hard exclusions, so that different philosophies of selection can be applied by different teams and compared. Selection functions become public maps that say for each patch of the sky, and for each class of object, how likely survival is through every cut. Counts then carry inverse weights that reflect those maps, so that the ledger becomes an average over opportunity, not a harvest of the easy. He sketches how these changes reach the headline. The number per square degree down to a chosen limit is measured over far larger clean areas with full covariance from tile to tile, and the multiplication by the sky inherits smaller error bands from both chance structure and masking. The faint end of the luminosity distribution at intermediate times is traced by many independent fields, rather than by a few pencil beams and the range of plausible slopes contracts. Diffuse galaxies that once slipped under the surface brightness floor appear in deep stacks and in tailored reductions that protect slow light, and those detections restrain the bias that once softened the faint end by neglect. Early counts are anchored by wide infrared spectroscopy that confirms distances for curated sets, and by millimeter detections of cooling lines that secure others, so that the fraction of imposters in the first billion years falls and the fitted curve stiffens. Energy balance across wavelengths tightens as Euclid and Roman resolve more of the near-infrared background into discrete sources, while long wavelength surveys account for a greater share of the far infrared glow, reducing the residual that once hinted loudly at missing populations. He keeps a measure of caution. Better instruments will not erase the fundamental dimming of surface brightness with distance, nor will they remove the longest waves of structure that no finite survey can fully average. Kernels will still have wings. Backgrounds will still vary. Pipelines will still draw lines between being and absence. The future counts will remain conditional only with conditions that are stated more completely and measured more often. The number will change as understanding changes, and it should, because a living census is a sign that the sky is being read with care. He permits a final speculation. If the true faint end continues to rise beneath present thresholds, the universe may hold a vast archipelago of ultra-diffuse galaxies and quenched dwarfs, whose stars drift so far apart that their light is almost sea foam, a quiet nation that shapes halos and tides while escaping most ledgers. If early galaxies remain more abundant than once thought, the first billion years may have been thick with small beacons, whose brief lives ionized broad volumes and spread metals, widely setting conditions for everything that followed. If intracluster light extends farther and holds more of the stripped history of groups and clusters than current models allow, then a significant share of starlight lives between galaxies and adjusts how mass, light, and environment are tied together. Each possibility carries the count in a different direction, and each waits on the next eyes and the next accounting. He ends with an unresolved wonder. The route from raw photons to a headline total passes through choices that cannot be avoided, and the proper act is to make these choices in the open and to test them from many angles. The next instruments will widen those angles and let the census include what it once culled. The count will climb or settle by steps, and with each step the ledger will speak more plainly about what is certain and what is not. Beyond the number lies the purpose that keeps the count honest, not to compress the sky into a single figure, but to understand which kinds of light are seen, which are missed, and why. The word billions remains true within its limits, and the larger truth remains just beyond those limits, waiting in gentle halos and dusty knots, and earlier sparks patient in the dim present in the web, and moving toward view, one careful decision at a time. He lets the noise fall away until only a steady hush remains, because after the long path through thresholds, masks and models, what lingers is the shape of a question, more than the shape of a chart. He rests the mind on the sky as one wide fabric woven from faint islands, and the dim light between them from early sparks pushed into the red, and from nearby halos that breathe softly against the background. He keeps the headline close and lighter than before hearing in the word billions, a promise, and a boundary at once. He sees the count as a living estimate that learns with each new field and each new spectrum honest about the lanes where it cannot yet travel honest, about the kinds of galaxies that slip along the margins. He recalls that surface brightness declines with distance in a way that cannot be bargained with, that glare breeds blind zones near the bright, that dust moves energy from blue to long wavelengths and hides the work of young stars, and that colour used as distance opens the door to abundance while inviting confusion. He holds, too, the gentle agreements that have gathered the faint end rising, where the data allow the diffuse background narrowing toward the sum of resolved and extrapolated light, the simulations bending toward the ledgers they once missed. He trusts the next instruments to widen the lanes without removing the need for care, and he accepts that even then the census will be conditional, because the universe is large enough to defeat a final inventory, and kind enough to reward a careful one. He ends where the search began, with the sky itself patient and intricate offering, just enough light for today's accounting, and leaving the rest in reserve so that curiosity remains a force and not a footnote. The number is a waypoint. The wonder is the road. The work continues, the mystery remains,